Hello, this is the video that corresponds to Chapter 3, Sections 3.1 and 3.2 of the text. What we're going to do, this is actually for the entirety of Chapter 3, will be Introduction to the Proof Method and 2 inference rules. So the proof method is another way of determining or proving argument validity. We did that using truth tables in Chapter 2. Now we're going to develop a second method for verifying that an argument is valid. So first I'm just going to give an introduction to the method. What is it basically, and kind of how does it work qualitatively? Then I'm going to introduce the first 2 inference rules, Modus Ponens and Disjunctive Syllogism, and work through some examples. The proof method hinges on these rules. Chapter 3 will discuss inference rules, Chapter 4 replacement rules, and they work slightly differently. But those 2 things, the inference and replacement rules, are the main player in the proof method. That'll be pretty much this video, will be these 2 things. Then in the subsequent videos, we'll talk about, well, actually, no, I'm going to talk about truth preservation also in this video as well. Then in subsequent videos, there'll probably be 2 more for Chapter 3. I will discuss the rest of these topics, 4 more inference rules, and then conditional proof. So this video will get at 1 through 3 here. So first topic, introduction to the proof method. So first thing we're going to do is we're going to represent arguments slightly differently from how we've been representing them so far. So far, this is how we've been representing arguments. We have premises and a conclusion that are all numbered. Premises are above the line, conclusion is below a line, and then there's a little triple dot here. We want to represent a proof or an argument slightly differently because we want to clear up space underneath the premises. So what we're going to do is we're going to move the conclusion off to the side of the last premise, and we're going to use like a little slash just to separate the last premise from the conclusion. So this is just kind of off to the side here. And then we're going to get rid of the conclusion and the bar. So basically, we still know what the conclusion is, but we've cleared up space underneath the premises. And the reason is we're going to be working underneath this space. Now, how does the proof method work? Well, first I'm just going to sort of show you a proof. Some elements of it aren't going to make sense, but it'll give you the basic idea of what we're going to be doing. So what we're going to be doing is using rules to derive new numbered lines from the existing numbered lines. And so far the only numbered lines we have are the premises 1 and 2. Conclusion is no longer a numbered statement. We've moved that off to the side and we've taken the number away. Okay, so the only numbered lines we're starting with are the premises. But we're going to derive new lines underneath the premises. And the goal is to eventually derive the conclusion. So derive a new numbered line that is the same statement as the conclusion. So in this case, we want to derive not E on a new line. So how would we do that? Well, so these were our first 2 premises. Now I'm going to write line 3 under here, and that's going to be not D. Where did that come from? Well, I used the rule of simplification on line 2. That's not going to make sense right now, but basically what this is saying is that I used a rule on line 2, and that rule tells me, basically what all the rules tell you, is that if you have certain sorts of things that you can apply the rules to, they will let you write certain sorts of things on new lines. So the rule of simplification will let me write not D if I have a conjunction and one of the conjuncts is not D, basically. So this is a new line. This is my justification. So I've got a new numbered line. This is the justification. This is the rule that I used and the prior line or lines that I used that rule on to derive my new line. And then I keep doing that. I can then get this by using the rule of disjunctive syllogism on lines 3 and 1. I can get G by using the rule of simplification on line 2. And then I can use Modus Ponens on 5 and 4 to get not E. Now eventually, you're going to do what I've done here. I've derived, your goal is to eventually derive the conclusion. So my conclusion is not E. And look, I derived that. Okay, so I got exactly the same statement. And that's your goal, because if you do that, if you can derive the conclusion, then that shows that the argument is valid. Okay, now I'm going to explain why that works in a minute. Okay, like why is it that just deriving the conclusion shows that the argument is valid? But before I get into that, let's sort of introduce the first two rules, how they work, and see a couple of examples. So here's the first two inference rules. The first one is Modus Ponens. We'll abbreviate that MP. And for every rule, you're going to get the name, an abbreviation. You'll get a sort of visual schematic like this that is just going to kind of remind you of the rule. And then also a verbal description of the rule. And the verbal description is in the book. I'll also just state it here. But what this rule is saying is that if you have a conditional on one of your lines already in a proof, and on another line you have the antecedent of that conditional. Okay, so the thing above the line on these schematics, this is what you would need to have in order to apply the rule. You need to have these two things already on numbered lines in your proof. So you have to have a conditional and you have to have the antecedent of that conditional. The thing below the line tells you what that rule says you can write on a new line if you have the components it needs. And so what this rule says is you can write the consequent of that conditional on a new line. Okay? So if you have a conditional and if you have the antecedent, then you can write the consequent on a new line. Okay? The second rule is disjunctive syllogism. And this rule says if you have a disjunction on a line and you have the negation of one of the disjuncts, and here we do, one of these disjuncts is phi, and here I have not phi. So I have what I need. The rule says then, if I want, I can write a new line that just consists of the other disjunct. Okay? In this case, psi. So if you have a disjunction on one line, you have the negation of one of the disjuncts on another line, you can derive a new line consisting of the other disjunct. Now notice a couple of things here. First off, what does it mean to have the negation of one of the disjuncts? Okay, so here we had a disjunction. One disjunct was phi, and then on the other line I had not phi. So this is the negation of that. Okay, and in the visual schematic, that was represented by having a tilde here but not here. But the important thing is that you can also have the negation of a statement if you have one less tilde. Okay, so phi is the negation of not phi. So this would also be a perfectly fine visual representation of disjunctive syllogism. Why? Because I have a disjunction, either not phi or psi. I have the negation of one of the disjuncts. Phi is the negation of not psi. So I can derive the other disjunct, psi. Okay? So in a lot of these rules, I'm only going to give you one schematic, but anytime there's a tilde, which indicates what that means is that this has to be the negation of that. But when you apply it, you can have the negation of something by either adding or subtracting one tilde. And we'll see some examples. Notice something else. It says that you just need the negation of one of the disjuncts. It doesn't have to be the first one. So look at this schematic. I have phi or psi. I have not psi. I have the negation of the second disjunct. And so I've derived the first, the other one. Okay? Here also, this is the negation of that. It's got one tilde difference, so that means it's the negation. So I derived the other disjunct, not phi, by itself. So all of these visual schematics are all different legitimate examples of this rule. You have a disjunction on one line, negation of one of the disjuncts, so you derive the other disjunct. Also, it doesn't have to be the case that the disjunction is above the negated disjunct. This could also work, right? I have a disjunction on a line, I have one of the disjuncts negated here, so I derive the other disjunct. Okay. With those two rules in mind, modus ponens, modus tollens, let's run through some examples. By the way, if what I was just talking about with disjunctive syllogism, the negations and everything like that, if that didn't make sense, work through some examples, like watch the examples I'll work through and go back to what I just said and it'll make a lot more sense. Okay, if it already made sense, great. But if it didn't, don't sweat it. Check out some examples and then go back. Okay, so here's a proof. We have two premises. If A and B, then C, and premise 2 is A and B. Conclusion is C. This is what I'm going to try to derive. I want to get C on a line by itself. This proof is really short. I can do this proof in only one step. And so what I'm going to do here is I'm just going to remind everyone of the rule of modus ponens. And in particular, what the rule of modus ponens says. So I'm going to sort of walk you through how I use this rule to get the conclusion. Okay? So first, for any derived line, if you're wondering how someone got that line, look at the justification. That'll tell you how they got it. This says I use the rule of modus ponens on lines 1 and 2. So here's the rule of modus ponens. And what I'm saying, what this justification says, is that this rule can apply to 1 and 2. So now let's look at the rule. This rule says I need two things. I need a conditional, and I need the antecedent of that conditional. Well, sure enough, if you look at line 1, I do have a conditional, right? So far I've got, so far so good. I've got one of the things that this rule says I have to have. So I have to have a conditional, but that's not all. I need one other thing. What do I need? I need the antecedent of that conditional. Okay, if phi then psi, and I've got the antecedent here. Well, look, I've got the antecedent of that conditional right here. So I have the two things the rule says I need. I've got a conditional. I have the antecedent of that conditional. Okay, I have both of those things on their own lines. Since I have what the rule says I need, now the rule tells me what I get to do if I want. And this rule says that if I have those things, I can write a new line that consists of the consequent of that conditional. Okay? So what I did is, here's the consequent, and I just wrote that consequent on a new line. So this is just exactly what the rule said I could do. Okay, so I'm using the rule of modus ponens on 1 and 2 to derive 3. Okay, now this proof, and I'm done because I've derived the conclusion. All right. This proof was super easy. This was only one step. Very few proofs are going to be one step. Now note something. This came up in chapter 2, but it's relevant here. We're still using Greek letters as statement variables that can stand for either simple or compound statements. So when this says, I need a conditional if phi then psi, the reason we're using these Greek variables is because phi and psi, they might be atomic. This should be atomic. That's a synonym, simple and atomic, but I'm trying to be consistent with my terminology and just use atomic, so I should change this. But anyway, they could be atomic, so here psi is playing the role of C, but they could also be compound, because here phi is playing the role of A and B, which is a compound statement. So that's why we're using the Greek letters. Okay, let's do another proof. So here we have three premises, and the conclusion is not Q. So what I'm going to do is, we only have two rules so far, and I'm going to write these rules down here. And we're just going to apply the rules up here. The goal is to derive not Q. So is there anything that we can see where we can derive this? I mean, let's take a look. can we use modus ponens? Modus ponens says we need two things. We'll need a conditional and we need the antecedent. Well, here's a conditional. If we had the antecedent, we'd be in business. The antecedent is P, but look, we don't have P on a line by itself anywhere. So we can't use modus ponens. If we can't use disjunctive syllogism, then this is going to be a short example, but fortunately we'll be able to. Let's see where. Disjunctive syllogism, also we need two things. We need a disjunction and we need the negation of one of the disjuncts. Do we have that? Well, we have a disjunction. Do we have the negation of one of these? Yeah, right here. This is the negation of that, okay, because it's just one tilde difference. That's not Q and this is Q. So we have the two things that disjunctive syllogism says we need. What does disjunctive syllogism says we get to produce if we have those things? It says we can produce the other disjunct. If we have the negation of one of the disjuncts, then we get to write the other one on a line by itself. So here's my disjunction. I have the negation of the first disjunct, so I can write the second one on a line by itself. And my justification was I used the rule of disjunctive syllogism on 2 and 3, because 2 and 3 are where these two things are. Okay? So this is my justification for that. All right, now we're not done yet. We want to get not Q. We don't have that yet. We have to keep going. Now, is there anything else we can do? Can we do disjunctive syllogism again? Well, we still only have one disjunction. We have the negation of that. We already did that. We don't need to do it again. We could, if we wanted to, by the way. If you wanted to, you could write line 5, P, by 2-3 disjunctive syllogism and just get P again, right? Now, I'm not going to do that because that's not going to help us. I've already got P. But you wouldn't lose points if you did that because it's not a mistake. It's just a waste of time. Look, though. Now we can use modus ponens because this thing we just derived P, this is the antecedent of this conditional. So now we have the two components that modus ponens says we need to have. We need to have a conditional, we need to have the antecedent of that conditional, and we do. We have a conditional on 1, we have the antecedent on 4. So those are the two lines we're applying the rule to. What does modus ponens says we can produce if we have those things? It says we can write the consequent of that conditional on a new line. So here's our conditional, here's the antecedent, what's the consequent? Not Q. So I can write a new line with not Q, and here's my justification. I use modus ponens on lines 1 and 4. So I use this rule, and the things that the rule says I needed in order to use it, I can find on lines 1 and 4. And then I produced line 5. And now I'm done because look, this is the conclusion. So I managed to derive the conclusion using the rules. Let's do one more example. Here's another argument. We have 3 premises. Conclusion is not C. We only have 2 rules, so I'm just going to put both of those rules down so we can, refer to them as much as we need. Let's just go and see what we can do. Can we use modus ponens? Well, we'd need a conditional and we'd need the antecedent. Do we have that? Yeah, here's a conditional. The antecedent is not A, and we've got not A up here on line 1. So we could use modus ponens. Can we use disjunctive syllogism anywhere? Let's just look and see. We'd need a disjunction and we'd need the negation of one of the disjuncts. So we have a disjunction and we'd need the negation of one of the disjuncts. So we'd either need C, we don't have that, or we'd need B, we don't have that. Okay, so we can't do disjunctive syllogism, but we can do modus ponens. So let's go ahead and do that. So I'm going to do modus ponens on 1 and 3. I have a conditional, I have the antecedent of that conditional, so I can derive the consequent on a new line. Okay? But now notice, now I've got what I need to use disjunctive syllogism. I have a disjunction, I have the negation of one of the disjuncts. This is the negation of the second disjunct. Okay? So by disjunctive syllogism, I can write the other disjunct on a line by itself. That would be not C. So I use disjunctive syllogism on 2 and 4. to get not C, and now I'm done because that's the conclusion. Okay, so I'll just get rid of those rules because we don't need them now. And now the proof is done. So now you've got a basic idea of how it works. We've only got 2 rules, and the proofs we've done haven't been super complicated. They've only been 1 or 2 step proofs. As we get more practice and we get more rules going, the proofs are going to be longer and a little more difficult. But they're basically going to have this structure. You're just deriving new lines using the rules, and you're going to try to get the conclusion. What I want to do now, just to close out this video before I make the next video for sections 3.3 and 3.4. Now let's go back and ask, why does this method work? Why is it that if we can derive the conclusion from the premises using these rules, that shows that the argument is valid? The key of that explanation is this. The rules that we have, the inference rules, which are in Chapter 3, and then the replacement rules that we'll get in Chapter 4, all of the rules are truth-preserving. They have this feature. They preserve truth. What does that mean? That means if you apply the rules to only true lines, if everything you apply the rule to is true, it's only going to produce true lines. Okay? Now notice that for inference rules, it doesn't matter what happens if you apply them to lines that aren't all true. Okay? Doesn't matter. What matters is, in order for something to work as an inference rule, what happens if you apply it to true lines. And what needs to happen is it has to produce true lines. If the stuff you're applying it to is maybe false, it doesn't matter if it produces true things, false things for inference rules. Okay, for replacement rules it does, we'll see. The one thing it needs to do is, if you're applying it to true lines, you have to guarantee that the things you're going to produce are true. Now what does that mean? Why is it that feature tells us that an argument's valid? Well, here's a proof. These are our premises, here's the conclusion. Okay. And you can see that, don't worry, we haven't introduced some of these rules yet. But the proof ends with not E, which is the conclusion. So this proof is good, right? This shows that this argument, these premises, therefore this conclusion, it's valid. How does it do that? Well, we're starting off with just these 2, and then we used a rule to get this one. Now the rule is truth-preserving, which means that if these are true, then this has to be true. Okay? We used a rule on these lines. In fact, we only used it on this line in this case, but these were the set of rules that we were looking at to apply the set of lines, statements we were looking to apply the rules to. If these are all true, then this has to be true, because the rule is truth-preserving. Well, then we got this line, and we know that because the rules are truth-preserving, and we applied them to the stuff that was above this, if these are all true, then that has to be true. And then when we got this one, if all of this stuff is true, then this has to be true. And then when we got this one, if all of these things are true, then this has to be true. Okay? So if you think about it, what this means is that if the premises are true, then all of your derived lines have to be true, because we got them with truth-preserving rules that were applied to true things. So if the premises are all true, then every line we derive from those using the rules is going to be true. And we managed to derive the conclusion. That's our last derived line. So that means that if the premises are true, the conclusion has to be true. And that's the definition of validity. Okay? So that's why this method works. It's because of the definition of validity and the fact that the one feature that a rule has to have in order for us to be able to use it in the proof method this way is that it has to preserve truth. And all of the rules we have preserve truth. Now here's another way to think of it. Basically, I sort of showed you this way, which is that You can think of these rules as building a sort of bridge of truth from the premises to the conclusion, right? Because they all preserve truth. You can also think of it in terms of truth tables. So here's an argument. This is one of the arguments we just did, actually. Now imagine I'm going to rewrite, here's the premises, here's the conclusion. I'm going to do a truth table. A, B, and C are the atomic statements, whatever. These are the premises, okay? And I'm sort of outlining the premises in red here. Okay, that's premise 1, premise 2, premise 3. Okay. Now, let's look at all of the rows where all of the premises are true. And it turns out, in this case, there's only one row, but there, with other arguments, there might be 2 or 3 or, whatever, any number of rows where they're all true. But let's just focus on the rows where the premises are all true. And here there's only this one. A truth-preserving rule means that if I derive a new line, so I get B by modus ponens on 1 and 3, if I add B here, then the rows where the premises are all true is also going to be a row where my new derived line is true. So it's just going to extend this row of truth from the premises to this derived line. Any row where the premises are all true, my new derived line is also going to be true. And when I get not C, let's go ahead and put that here. Because it's a truth-preserving rule, wherever everything before that was all true, the new derived line is also going to be true. So I've just extended this truth row from the premises through all of the derived lines, which means that any row where the premises are all true is also going to be a row where every derived line is true. And since you derived the conclusion, any row where the premises are true is going to be a row where the conclusion is also true. See? Because this will extend all the way out to the conclusion. And if any row where the premises are true is also a row where the conclusion is true, then there won't be a counterexample row, right? You won't be able to find a row where the premises are all true but the conclusion's false. Okay, that's not going to happen. And since there's no counterexample row, the argument's going to be valid. So to summarize, because the rules are truth-preserving, any row where the premises are all true is going to be a row where any derived line, or any line derived from the premises, will be true, including the conclusion. So there can't be a counterexample row, so the argument will be valid if you can derive the conclusion. More generally, just think this is a truth table for some random argument. We don't know what it is, but these are the premises, phi 1, phi 2, phi 3. Okay, and suppose I do a truth table. We don't know what these are, right? There's some compound statements using A, B, and C. Suppose these premises are all true. These are the rows where they're all true. All of the rest of the rows, there's some mixture of T and F, but they're not all true on any of these rows. These are the rows where they're all true. Because the rules are truth-preserving, these are the derived lines, derived line 1, 2, 3. Every time I derive a new line, it's also going to be true on any row where the premises were all true. So every time I derive a new line, that truth is just going to extend on all of these rows until I get to the conclusion. The conclusion, if I can derive it, I know is going to be true on any row where the premises are all true, which means there isn't going to be a counterexample row, which means the argument's going to be valid. Okay? Now you might wonder, hey, what if there's no row, right? What if I did the truth table for the premises here and they were inconsistent, right? Suppose there's no row where they're all true. So there weren't any gray rows here, right? Remember what inconsistent means. Statements are inconsistent if there's no row where they're all true. Suppose your premises are inconsistent. What does that mean? Well, you're still fine, right? If you can derive the conclusion, the argument's still valid. Why? Let's walk through the reasoning. Okay, the other possibility is the premises aren't consistent. So there's two options. The premises are consistent or they're not. If they are consistent, then this is what's going to happen. If they're consistent, that means there's at least one row where they're all true. Any row where they're true, you're going to extend that truth out to the conclusion. You won't find a counterexample row, so it's valid. So that's one possibility. Premises are consistent. You won't find a counterexample row because even though there are rows where the premises are all true, the conclusion is still going to be true on those rows. Okay, so you won't find a counterexample row. Suppose the premises aren't consistent. So you have premises, you derive the conclusion, but in this case, your premises weren't consistent. You're still not going to find a counterexample row because the premises aren't consistent. There won't be a row where the premises are all true. And a counterexample row would be a row where the premises are all true and the conclusion's false. Okay, so either way, if you can derive the conclusion, you've ruled out the possibility that there's going to be a counterexample row. Okay, so that's why this method works. Okay, so that's it for this video. Hopefully by now you have a basic idea of how the method works. You use the rules to derive new lines from the premises until you can derive the conclusion. And now you have an idea of why it works. It's because these rules preserve truth. Okay, next up after this will be another video probably on sections 3.3 and 3.4.